For thousands of years, humans watched birds and dreamed of joining them. We built kites and sketched wing designs, but without engines, we remained firmly on the ground. That changed on December 17, 1903. Orville and Wilbur Wright solved the core physical puzzles: the mechanics of lift, the precision of control, and the thrust of power. Their 12-second run over a beach in the Wright Flyer proved that sustained, powered flight was finally possible. The World Wars accelerated engineering at a staggering rate. Aircraft grew faster and stronger, transitioning from wood and canvas experiments to reliable metal structures capable of massive industrial scale. After the wars, aviation became a business. Aircraft like the Douglas DC-3 made passenger and mail transport profitable for the first time, turning the airplane into a viable tool for global commerce. In the 1940s, visionary pioneers like Frank Whittle introduced the jet engine. By replacing pistons with jets, aircraft could fly higher and faster than ever before, permanently changing our relationship with altitude and speed. This technology led to legends like the Boeing 747. As the queen of the skies, it helped democratize travel, making international flights affordable for ordinary people. For those first 80 years, aviation was a test of mechanical resilience and human intuition. The airframe survived because it was over-engineered metal, and the flight succeeded because the pilot had the physical skill to manage the machine. This chart plots the locus of control over time. For decades, it stays flat. Then, in the 1980s, a sharp pivot towards digital systems. With the A320 and 787, the industry faced a dilemma: prioritize pure flying skill or total system optimization. Purists argue that these digital tools remove the flying from aviation. Engineers counter that computers are necessary to eliminate the physical errors that humans are prone to making. To understand which path is right for your goals, we have to look closely at what was gained and what was lost in the transition from classic aluminum to modern smart planes. In our comparison table, look at the classic control system. It relies on a physical link: cables, pulleys, and hydraulics connected directly to the pilot's yoke. This provides tactile feedback. They physically feel the aerodynamic resistance pushing against their hands. However, wrestling a heavy metal airframe through turbulence for hours is physically exhausting. The safety of the flight relies entirely on a human maintaining precise coordination while battling fatigue. Modern aircraft use fly-by-wire. Here, the pilot's inputs are sent as electrical signals to a computer, which then decides exactly how to move the flight surfaces. This results in incredibly smooth flight paths and automated protection. The computer won't allow maneuvers that would stall the plane or overstress the airframe. While this guarantees systemic safety, it changes the pilot's job. When the computer handles the 1,000 micro-adjustments once done by hand, the pilot moves from being an active participant to a passive observer, which can lead to a dangerous drop in mental engagement. Looking at construction, classic airliners were built with heavy aluminum structures and pushed by early fuel-hungry jet engines. These airframes were incredibly rugged. They were over-engineered to take physical punishment, often surviving minor ground strikes or heavy landings with just a simple metal patch. But that durability came with a weight penalty. Heavy planes burn more fuel, and the millions of rivets holding the aluminum together require constant, labor-intensive manual inspections for fractures. Modern planes are built from lightweight carbon fiber composites and powered by highly efficient turbofans, equipped with sensors that feed data to AI maintenance programs. These materials make the plane much lighter and allow for higher cabin pressure, reducing jet lag. Operators can even use predictive maintenance to fix parts before they actually break. But efficiency has its own costs. Repairing composite materials is far more expensive and requires specialized cleanroom environments and curing processes that traditional aluminum hangars simply aren't equipped for. In the cockpit, classic navigation relied on analog dials, radio beacons, and physical paper charts spread across the pilot's laps. Pilots had to be visually and mentally engaged with their surroundings, constantly translating needle positions and radio pings into a mental map of their position. That mental load is high. In heavy weather, a pilot must look away from the window to verify a chart, then back at a vibrating dial, then solve a math problem to estimate their turn. This constant division of attention makes it much harder to maintain a clear mental picture of where the aircraft is in relation to the ground. The modern glass cockpit uses a flight management system and GPS to consolidate all that data onto a few high-definition screens. This technology provides pinpoint accuracy. Algorithms can calculate the most fuel-efficient route possible, allowing for performance-based navigation that old radio beacons could never match. However, these tools turn pilots into IT managers. When the screens provide conflicting data or a sensor fails, the crew must rely on deep systems knowledge to diagnose digital faults rather than their eyes. To decide which path fits you, look at this quadrant chart. The horizontal axis measures your desire for tactile control against system optimization. The vertical axis plots your risk tolerance against your need for efficiency. You might be someone who prioritizes the romantic, tactile art of flight, the feeling of the wind on the wings, and the development of raw physical intuition. That places you here, in the classic path. This is the world of general aviation, bush flying, and the restoration of historic aircraft. Choosing this path means accepting higher operational costs and the reality that you are flying without the safety nets provided by modern digital systems. Or you might prioritize moving millions of people safely, optimizing every gallon of fuel, and working to eliminate human error from the cockpit. That identifies the modern smart path, which is the standard for commercial airline pilots and modern aerospace engineers. In this role, you must be comfortable acting as a manager of a complex data center, where your ability to diagnose a system is more critical than your physical coordination. Aviation has evolved. We have moved from a century defined by the struggle to conquer the sky to one defined by the effort to move through it with matched systemic perfection.